Andrew. So good evening, everyone. I'm Tim Hitchens, the president of the college, and welcome to those of you who are physically here this evening in the Leonard Wolfson Auditorium. Thank you for coming. Hello also to those of you watching this live on our YouTube channel, and hello also to those of you in 2050 watching this on the YouTube channel when you will be in a position to know exactly what is happening to Wolfson's commitment to zero carbon. So we planned before the project began this summer to have a presentation for everyone on what the programme would involve, but sadly COVID meant that was not possible. But we are lucky enough today to have with us a number of people who've been involved with both the design and the implementation of the project. We have people from the engineering side and people from the architecture side. So particularly we have Bill Watts from Max Fordham, who have been the engineers of this particular project, and also Andrew Dawson and Marion as well from Original Field, who've been our architects. And in a way, the fact that they're doing this, as it were, halfway through this phase means they're able to reflect not just upon the plans, but some of the realities of bringing the programme together. So we're going to have presentations for something like half an hour. Those of you here or on YouTube in real time are very welcome to ask questions. On YouTube, if you want to just insert a question into the chat function, then we can recount that back to the participants here. So without any further ado, Bill, would you like to come forward?
Thank you. Well, Wolfson College, great college. So I'll just start off by giving you a little bit of context. I won't spend too long on it, but the climate change and biodiversity emergency are two separate issues. Climate change is what we've been hearing a lot about in COP26 and things like that, but there is also a biodiversity emergency which is to do with land take, pollution, and other things like that. We need equally to be mindful of both agendas. It's quite possible for us to deal with the first agenda in the first world and trash the rest of the world and not leave any renewable resources for the globe as a whole. But it's important that everybody has access to whatever offsets are required or whatever renewable energy is required. So it's very important to think first in terms of it for a zero carbon agenda. First of all, you really must reduce your energy usage to the minimum that is feasible, and then use renewable energy or offsets to consume the energy that you need to carry out your business. So Wolfson's response to the climate change emergency. First of all, let's measure how much energy the buildings are using. We've got the blue bar at the top is how much electricity is being used, and it's a sizable amount, but it's not the biggest. The next two bars, two elements of the bars are gas for hot water production, and the grey bar at the bottom, the brown bar at the bottom is heat, which is by far the biggest element. Which is not surprising given that it's basically a glass and concrete, very elegant box. Now, the carbon context is where carbon and energy interrelate with one another. The units up the side are how many kilograms of carbon are emitted for every kilowatt hour of energy produced. Gas is a constant due to the chemistry of burning methane, which is CH4, whereas electricity can be made in a variety of ways. In the past, it was used by burning coal. The rapid fall in the carbon intensity on the blue line is the decommissioning of coal-fired power stations. And going on to 2050, this is the government's projection of how much electricity is going to emit in carbon. And it's reducing due to the onset of more use of renewables and nuclear power and things like that. So you can see that right now, electricity is becoming greener, if you like, than gas. And that's where this is going. This is the agenda we're going for. So our agenda, our brief for Wolfson and for decarbonisation generally, is to reduce heating loads, reducing the hot water loads, that's the water used to wash your hands, if possible, and to move from gas to electricity as your energy source. But this should be done at minimum cost, and to do that, we were looking to reuse as much of the existing infrastructure as possible, so nothing is wasted. So get rid of the gas. That's the before. So you've all been in buildings, in rooms which have got single glazed original windows, which are a little bit leaky, and it loses a lot of heat, basically. So I don't need to tell you anything about that. But you're kept warm with a gas supply that burns gas in some boilers, which push hot water around the building and into radiators in all your rooms. So the first step that we took was to analyze where the heat is going to keep you warm. This is assuming that everyone's at a nice temperature in their room. Where does that heat go? And the bar here, which is split into several colors, is a breakdown of where that energy goes. The lion's share of it is through the windows themselves, but also the heat loss associated with the windows are also considerable. This is the amount of heat that's lost around the edges of the glazing, through the walls and the concrete on the ceiling and the floor, which isn't necessarily through the window itself, but it's around the edges. And this part is to do with the ventilation because the windows are leaky. So Andrew's going to be talking in more detail about how the windows came to be what the choice of windows that we got at the moment. So that will come on after me. But just a brief outline of what the fabric's about. This is the current situation where you've got single glazing here, and you've got, these are solid blockwork walls here, and you've got a concrete floor here, and heat can not only go through the glass, it can go scoot around the edge of the glass and the window frame, and quite a lot of heat is lost through that. So if you're going to change the windows here, you also need to change the frame that it sits in and all the building around it. So we've insulated the walls coming back to prevent the heat scooting around the edges of our nice new windows. This is a cascade, a waterfall diagram of where those heat savings are taking place. The baseline scenario is here, giving us a 283 kilowatt hours of heat per meter squared per year of heat. That's what we need to put in to keep the building in its insulated state warm. We insulate the windows, and that takes off a good, well, nearly 50%. Then the thermal bridges, which is the term of the going around the edges. And then you've got the roof, which is a bit more, and you've got down to about 20% of the original heat loss. So, very good. As far as the hot water is concerned, it's a different story. It's not so easy to deal with that because of the geography and the layout of the building. The amount of water, the amount of heat that you need to heat the water that comes out of the taps is actually quite a small proportion of the heating required for the hot water. Most of it is used keeping the hot water warm as it's servicing the different taps around the building. And there are things that we can do to reduce that, but it is not as dramatic as the fabric of the main heating load. So now, moving on to away from the fabric and the heat losses and onto how we are producing the heat. Currently, it's using gas. So, as a review of how to deliver a unit of heat, doesn't really matter what that unit is, it's just one unit of heat. You can burn some gas. You would need 1.2 units of gas. 20% of the gas would be wasted, or the heat from it would be wasted up the flue and losses in the boilers and things like that. You could use an electric fire, and that all of the electricity would go into heat. There's no losses. Or you can use a heat pump. Now, a heat pump is a particular technology. It's the same as used in the fridge and things like that, where you take heat from a low temperature source and pump it up to a high temperature where in our case, it's useful. The electricity is needed to drive a compressor, and you need a source of low-grade heat that feeds the heat pump system. That's a quick schematic of what a heat pump looks like. You've got the electrical power coming in to drive a compressor that takes low temperature, low pressure gas here, compresses it so it's hot. The heat is taken out of that high temperature and pushed around the existing radiator system. It comes round through the condenser, except this isn't a condenser. I'll come on to that here. But then it turns into a liquid, low temperature liquid, where it uses low-grade heat to boil off and collect the heat from the low-grade source, and the circuit continues. This is quite an important aspect of what we're doing at Wolfson. We're using CO2 as the refrigerant, which is the fluid that's going around here. CO2, you might think rather ironically, has got a very low global warming potential in comparison to other refrigerants that are available. CO2 has a GWP of 1, and the other heat pumps and refrigerants you get are anything from 600 up to 2,500. So it is a very green refrigerant. The other aspect of it is that it doesn't actually condense in the condenser. It comes in as a high-pressure gas, very hot, and leaves as a low-temperature gas. And to get the heat out of it, you need to cool it down over a wide temperature difference. So it can produce water at the high temperatures that the boiler can produce it at, but in order to be efficient, it needs to have water coming back to it at 30 degrees or something. So in reusing a lot of what the work and thinking that went into this project is how to do that with the existing heating system. So the choice of heat source, I won't dwell on this too long, but the low-grade heat can come from a number of different places. We have chosen to use air coils, which you will see popping up around in the car parks. And these air coils basically take outside air and push them across some fins because you've got low temperature refrigerant inside the air coils. It cools down the air by 2 or 3 degrees and then blows it out in the same direction. So these will be in these positions in the car parks and blowing air, sucking air from the car parks and blowing it out through these grills here. And they'll look something like that. They'll be a bit darker grey than that, but that sort of arrangement, and they'll be screened off. So now to the radiators. And the reason, this is why I spent a bit of time talking about the transcritical CO2 cycle. The heat, so the existing system, when I say existing, the system as was, the water from the boilers came in at about 60 degrees through a thermostatic radiator valves that you could control, and then left a bit cooler, but not much cooler. But the average temperature of the radiator was about 48 58 degrees at peak conditions. Now, in preparation for operating with the CO2 heat pump and the transcritical cycle, we have put temperature limiting valves here to limit the temperature of the water coming off the radiator. So now they've all been set to about 40 degrees. We still have a thermostatic radiator valve here, and this will adjust the temperature of the water coming in. We can get water quite hot coming into the radiator, and with this temperature drop between 75 and 40, you can still have an average radiator temperature of 58, which is the same as what it was before, but you've achieved it with a much bigger temperature drop across the radiator. Now, that's fine in the old condition, but in the new condition, after you've insulated your room, you need a much lower average temperature. So you'd still have the water coming in at quite a hot temperature, but it will be going off at a much lower temperature, which is appropriate for our heat pump and make it very efficient. So just to recap on that, all the rooms will have, this is a picture of a room. It's got 2 radiator valves. You've got one which is available for the resident to turn and adjust, and depending on what temperatures you're looking for. And at the other side, you've got what's called a return temperature limiter, which will be fixed, and at some stage before March, we'll be resetting it to an appropriate level for your room. Basically, the less heat loss your room will have, the lower we will set this. So it'll be set somewhere between 25 and 30 degrees return. But what I'd like to reiterate here is the better insulation means less heat loss. Less heat loss means you need less heat coming out of the radiator. So if you're warm and the radiator is cool, it's working. And you should pat us all on the back because we've achieved something. So this is a little schematic of where we are at the moment, what the proposals are. We need a new enhanced electrical supply, which is what you might have noticed some digging going on around here. That's going to have a whole bunch of cables in it. The heat pumps are here. You've got the 4 air coils there, and hot water surrounding the building, going out to the building, but cooler water, much cooler water coming back. And the overall impact on the carbon, here's another waterfall diagram, the fabric, and this is over 20 years, the reduction in carbon from our business as usual falls away like this with our residual footprint here. Okay, that's me, thank you. Andrew, would you like to tell us all about the windows?
Thank you, Bill.
Okay.
Hello, my name's Andrew Dawson from Original Field, and in the front row is my colleague Marion Brereton. Marion has been an architect working at Wolfson for many years and is the author of this fine establishment or building we're in now. Bill has set up the parameters for the building science, and with him we developed a set of performance criteria that we had to respond to. Glass performance, airtight quality around windows and so forth. That was fine, but our biggest challenge was the buildings are grade 2 listed, and as a consequence of that, any alterations to the existing building fabric requires approval, the relevant approvals in place. And in doing that, we needed to consult various regulatory bodies, including Historic England and the 20th Century, the 20th Century Society. The 20th Century Society are the custodians of Britain's 20th century buildings. And when we met them on site, they were not particularly happy about altering any part of the buildings. In doing that, we had to establish what we were going to do to the buildings within Bill's framework of responding to the building science, but also with a deep understanding of what the existing buildings were. So at the beginning, we had to go through a process of understanding what the windows were, because the windows were the main element that we were affecting. And in the beginning, we had we set up this menu of windows, and you can see at the top we had type 1 windows, which are the horizontal sliders. Most of you are familiar with those in the bedrooms. And then the type 2s are the vertical sliders, which you see on the north elevations of B and C block. And then we have miscellaneous types all over the complex of buildings. It is quite complex in terms of the number of windows, the types of windows, the various junctions and so forth that happen as a consequence of the windows. So we were quite fortunate. The college has quite a good archive of original drawings, and these are examples of details that we had. These details allowed us to gain a thorough understanding of the junctions and the relationship between different elements and so forth. One of the problems is that as we improved the thermal performance of the window, we had to look at the specification of the window, and that did have an impact on what the size of the window is, the position of the window, the width of the sight line or the loss of the sight line that we had to have for the centre mullions. So this was all part of the negotiation of trying to satisfy the requirements that Bill set out at the beginning of the project, and also appeasing the planners and the conservation officer. And they were interested in everything from the colour through to the relationship with the existing building. The mullion thickness was a big one that we had to go through. And they did make us revisit a number of windows, and not the main windows, but mainly the horizontal windows here. As we progressed through it, we started to look at the sketch design, and we started to think about, we had to start looking at what windows we could use, the mullions, the glass and so forth, and thickness. So there was this sort of iterative series of steps that we went through to proceed with the design development. And all along the way, we were working with Bill, and Bill was keeping us in check in terms of the detailing. We got to the point where we had to do technical development, and this was still before, or just before we went to planning and listed building consent. So we have to resolve a high level of detail, and you can start to see here, this is a cross-section through a window, and you can see what Bill referred to earlier as this sort of portal surround around your windows in your main bedrooms. And we started to then, once we've got listed building consent, we had to then move into the next stage, which was production and fabrication drawings. So each element within the windows, and the windows being the main production element, had to be drawn with a level of precision that then they could be fabricated within a factory. At this stage, we started working and collaborating with some collaborators. We were working with Fenster. You would have seen these guys around the campus and their signs. Fenster are a glazing fabricator and installer. Benfield and Loxley were the builders. They built the auditorium here and have been working on the campus for many years. And Alden are the incumbent mechanical and heating engineers on the campus. So once we'd done all the fabricated drawings, we then went into production and then the installation process. At the beginning of the project, we all sat down and we thought that the project would require this rhythm, an installation or a rhythm of installing the building. We had quite a defined set period of getting into a room, taking the window out, and then installing the window, and then coming along and doing the builder's work and the surrounds. This was all set up and designed specifically so we could get in very quickly and get out very quickly. With this rhythm, there was no contingency. And within the building industry at the moment, there are many challenges, and this was not without its challenges. On Block B was our first building. We encountered a lot of problems that disrupted our rhythm. And in particular, one is the supply chain within the construction industry. All projects within the UK at the moment are experiencing difficulty with the supply of materials as well as labour shortages. However, we have encountered significant problems with the supply of glazing and aluminium in particular, and that's the main components of the windows. So I think you've probably experienced that we've got onto Block C, we've got our rhythm back. So the rhythm has been working really well on Block C, and that will hopefully continue through into Block E. That's about it. I could talk more, but I'm sure there'll be lots of questions.
You want to... There we go. Great. So thank you both very much indeed. And now's an opportunity to ask any questions. I've got a few that people have asked me, but is there anyone, first of all, around here who would like? Okay, now I wonder, if, for people outside, I wonder if you could have the microphone and just say your name first, and then we'll try to answer.
Hello. Good, that sounds nice. I'm Igor Dyson. I'm an engineer, and thank you for a fascinating talk. I was just curious that you showed a variety of heat sources, including river. So I'm wondering, well, if I could see the slide again, or if you could explain why did you choose air in particular, please? Thank you.
Yeah, thank you very much for the question. Some time ago, I would have said, wow, this is great. Oh, you've got all these opportunities. Why don't you use the river? You know, but then you come to look at exactly what you need to do that. And a lot of the work that I do is quite aspirational. And I'll get on to the real reason, but this is a sort of context that a lot of things seem like a good idea, but actually when you come to dig into all the stuff that you have to do to make it work, you quickly realize, I don't think I should have started this process. So that's the context with which I'll answer this question. The river is an excellent source of heat-ish. It's water, it's dense, and it probably doesn't freeze, but it might. If it does freeze, you've got a problem. The water is quite clean, but not totally clean. It will need some sort of filtration. It will need something to keep the fish, the shopping trolleys, the stuff out of it. And then you'll need, you will need some planning conditions about putting something in the river to suck water out of it. If you're going to pull the water out and pull it into a heat exchanger. So the combination of the filtration, the planning, all of those issues meant that I wanted to give that one a miss. The other way of doing it is to lay pipes up and down the river, and you'd need a hell of a lot of them. And then you need to keep them clean. So you've got somebody, you get Chris in his waders going up and sort of scratching away at I didn't want to put people through that. And so the air source is boring, I'm sorry, but it works, and yeah. And I know exactly what, defrosts, it needs cleaning every now and again. It just works, I'm sorry.
Thanks, I get the picture.
About ground source? And
ground source, it also works. It's just adding another, it is expensive, because you could imagine you would need, I think it was something like 180 piles around the place. Oxford you've got to be very careful that you don't puncture the aquifer below. And,
I'm aware.
And it's more expensive, and actually, if you can imagine a piling rig spending 3 or 4 months wandering around the site drilling holes, that, again, I didn't see.
Thanks, I get the picture.
So keep it simple. Yes, I'm afraid we've got one down here. If we come down.
I can start.
I'm afraid for people elsewhere to hear your question, I'm afraid.
Kevin Martin. So the thing that you didn't get to is actually when you put your heat pumps and everything in, you're using more electricity. Presumably the kitchen is going to be running on electricity, so your electricity demand has gone much higher.
Yes, yeah.
And you're saying somehow that it's all going to be done by renewables, because that's presumably what zero carbon means. But renewables is essentially turbines and solar. Biomass is certainly not a renewable in a time frame that is meaningful. So, in fact, coal is probably better than biomass right now. So I just wondered what that kind of thinking was in when you were saying zero carbon, what should we believe to be zero carbon in your estimate? The other thing is, very interestingly, importantly, you pointed to this difference between climate and biodiversity as something we might also discuss. But the thing you were firm about, number one point, is to reduce your energy usage.
Yeah.
And people don't want to do that. And we heard nothing about how you actually can get people, although you've now got LED lights in, to switch them off, or all the other behavioral things they can do. And anybody who's lived in, Egg or Cape Town or so on understands behavior can make a huge difference in the energy consumption, and yet always we hear nothing about it. And in a college like this, it seems to me you have a golden opportunity to shape people's behavior, to really push the energy consumption down. And I just wondered what your thoughts are on your point one of reducing your energy use, because people are not going to do that voluntarily.
So answer the first, your last point first. I mean, in a way, people turn to engineers for solutions that don't require too much sociology. And I'm not stopping people turning down the heating or amending. There's very little climate sort of, you can adjust your heating according to what you need at the moment. I think when you say what could we do, I mean, Wolfson is actually a very good case example of something that has got a very high heating consumption that can be turned into quite a reasonably low one, because you know exactly where the heat is going. It's going through the windows and the concrete. And actually those interventions are not too difficult to do, notwithstanding all the work that's been going on. So I think it's absolutely the right thing to do. What you then can do with behavior on top of that is, if you run the buildings at 20 or 17, you will save more energy. There's no doubt about that. If you switch it off every time you go out the room, you would save energy. But we haven't put that additional complexity into the system at the moment to happen automatically. So it is up to the people to do that. So in terms of where does the renewable energy come from? Again, I mean, I've got a lot of views about that, but it's really not in my gift to determine where that energy is coming from. There's a government view that we want to decarbonize the grid. We're doing three things. So the gas, we're reducing the amount. If we kept the gas boilers, we would halve, by insulating the buildings and just operating them as they are at the moment, we would halve the gas use, and so half the carbon from using gas. If we then do that with electricity without a heat pump, at the moment you would use the same amount of carbon, presumably, but over time that would fall away if you believe the government. But by putting in a heat pump, you are reducing the amount of electricity you need by a factor of 2.5, something like that. So at the moment, the carbon intensity of the grid is similar to what gas is. So with nothing else, even if that didn't change from now on, we will be using about 2.5 times less CO2 than we would do if we were burning gas. So, but I do believe that it's possible to decarbonize electricity. It will be the cheapest form of electricity, I believe, in the future. There's a lot of discussion about where that's going to come from and how it's going to be transported around the world. That's a sort of geopolitical issue that is fascinating. But I don't know where exactly we're going to go with it. But basically, renewables are flying down in price. And it's just a matter of getting access to them by cables or hydrogen or something like that. They're not necessarily in the UK, but globally. Sorry.
Can I just add in this sort of on behalf of the college? What we were looking for was an engineering solution to take us part of the way. But as a community, we do have the ability to set behaviours and to set expectations. And we're a college that has so far been very keen to dedicate resource to this and time and energy to it. So I would definitely hope that there will be behaviour changes coming. And I suppose the other part of it is this describes, as it were, phase one of this project, which is fundamentally air source heat pumps and windows. But there is a second phase which not only extends that geographically, but looks at solar panels and batteries, which is starting down the road that you're describing. So, I mean, my experience is that zero carbon is always a final aspiration. You're never going to get there, but you can concentrate on scope 1 first, and then scope 2, and scope 3 will carry on forever. But this is a major contribution to scope 1 zero carbon.
Applause, absolutely. I live off grid, so I understand the problems of what happens in the middle of winter, like the weather today, no sun, no wind. And my point was about the renewables. Renewable is that thing if you're talking about biomass. Biomass is increasing the carbon loading every time you increase your electricity demand. So that's the equation really that the engineers haven't solved. And the behavioral thing is the thing in the equation that's always missing, because you could have a program like Zurich Canton has for a 2 kilowatt society, which means each person primary energy use is 2 kilowatts per person per hour. We're about 3 or 4 times that now in the UK. But there's a target and there's a way to get there, but it requires a huge amount of joined up thinking, and behavior in the college is one under your control.
Thank you. Any other questions? Is there anything particular, Jessica, you want to?
Thank you. I want to say, by the way, for all the information. This is really interesting to learn more about. We don't actually have any questions from YouTube, but I do have one myself. As you guys know, this is a living site. We have a large number of students who live here in college and who will be interested in the timeline of works as well as the impact these works are going to have on them in their daily lives. So for them, I've got a bit of a technical and disruption level perspective question. So to what extent are you able to retrofit the new heat pump system to the current existing framework? And is the aim for this to be completed within the same time frame as the window replacement, i.e. March of 2022?
Yes. The heat pump will be commissioned in February, March. Yeah.
You're able to completely retrofit it, is what I'm...
Sorry?
You're able to completely retrofit it to the current framework?
Yes, yes. I mean, it has to be said that, I don't know if you noticed, but the boiler, where the heat pump's going to go is separate from the boiler room. So the boilers can be left there indefinitely if you want to. So we can parallel run for whatever period of time, or we can just turn a valve and shut them off. So that's how it's going. So that shouldn't be apparent to anybody as it happens. But there are going to be little bits of changeovers here and there which will be apparent. But at the time, you shouldn't notice a difference between working on a heat pump or a boiler. It could be because all this preparatory work is with the boilers in place to get the system up and running so that it can be dealt with by the heat pump, hence all the radiator and the valves and all that sort of stuff.
Most of the equipment has been ordered, and yeah, we've had no indication of any problems with the supply chain. However, yeah, I think we've always got to be prepared that there are things happening out there that are beyond our control.
It's been amazing how well this project has gone, given everything. Anyway, sorry, just was.
Andrew, can I ask a question of you, which is, in some ways you were designing windows based upon some plans from 50 years ago. When you actually got rid of the old windows and the old surrounds, was it exactly as you expected, or were there some surprises?
When you look at the existing windows, they're incredibly fine in terms of them. Oh, sorry. When you look at the existing windows, they're incredibly fine. You can see this sort of slideshow showing them. And architects love that fineness. As soon as it starts getting chunky, that's when anxiety sets in. I think one thing that's worth doing is, and I did it one weekend when I walked past, is if you have a look at E-Block at the moment, they've just started doing the north elevation of E-Block, the student rooms. They'll start doing a few rooms. Have a look at the existing against what's been put in, and then try and negotiate and see what the differences are. There is one key difference. It's the depth of the centre mullion. On these, they're incredibly fine, but on the new ones, you start to see a depth of field where it is quite a bit more chunkier. But apart from that, it's pretty good. I think I'm pleasantly surprised. Marion, you might have something to say about that.
Yes, yeah, we're not surprised. I mean, Finster have been able to replicate, because we've taken essentially a standard window, but obviously Wolfson has fins and projections and mouldings that the Conservation Office and 20th Century Society wanted replicated. They don't exist in the industry, so we've had to have a hybrid to achieve that and to achieve that look. So when the sun hits it, you get the shadows that you previously had, and we don't get a very flat facade, which modern windows have nowadays.
So I'm just going to repeat that because we didn't pick that up on the mic. So what Marion's saying is that we have using a relatively standard kit of parts as far as the windows go, and these are off the shelf, but we put the components together to achieve it precisely what the original windows were. It's a totally bespoke system, and we would be fabricating aluminium profiles to achieve the profiles that we have on the existing. So we have had to negotiate changes in industry and so forth. But I think the outcome is very good. I mean, you can see for yourself when you have a look at Block E, and you see for yourself.
Can I ask a sort of sorry, I'll come back if I may, but can I ask a linked question, which is, if you are a college which has 16th century windows and buildings, are they going to find anything in what we've done that will help them do what they need to do, or is theirs just a completely different kind of project?
I mean, we've gone on this journey of looking at glass, for example, and we're using Kuhn glass, which is triple glazed. However, it's only 2 panes of glass with a film in the middle, and that's 1 millimetre thick. So I think there's going to be quite significant advancements in technology, in particular to do with the performance of glass. I mean, Bill's got a favourite, is your vacuum glass, which is incredibly thin, and I can see that actually evolving into actually replacing glass panels or panes in older buildings, and you can get it up to about 6 mil. If you can get it down to 4 mil, then that would be fantastic. So I think it is going to evolve quite quickly in the next 10 years in terms of the availability of materials that can be adapted and put into those situations. Whether the planners and the conservation architects or the conservation officers let you, that's another, they've got to give in. There's got to be a...
And in a way, that's been one of the joys of this one, is that we have managed to get the planners to recognise that the climate change case, in our case, is stronger than the conservation law, that one can balance the two.
Yeah.
Did you want to come back in with...
Sorry, I just wanted to ask about the water temperature issue, because 70 degrees presumably is to heat hot water, and you just then use the same temperature to use the radiators. Alternative would be to separate them, because you don't need the hot water for the radiators, but you need it for the washing. And then also the issue, coming back to the future program, is there going to be solar water as even a kind of preheating for the water system?
We needed, we only need 65-degree water for the hot water, the hot water, the tap hot water. The heat pump is pretty efficient. It can produce that without much degradation in efficiency, provided you get the return back cooler, unlike other heat pumps, which have got a very small delta T across them. And getting 65-degree or higher water temperatures is really inefficient. The point about this is that if we had rooms which didn't have any insulation in it, if we had another system which had only had a 5-degree temperature difference across it, then the whole system would have to run at that high temperature, and that would be quite a high consequence. There would be a loss of performance across the whole system. So I think this allows us to take the benefits of where the retrofit has happened, but still allow us to treat rooms that haven't been insulated. That's why that temperature difference is there. So there isn't too much of an advantage to separate the two systems out. The solar thermal stuff, in a way, solar thermal is one of those ideas that sounds good, but actually is tricky. And if we've got, my view about that is that if we've got solar PVs on the roof, we can use that energy in the heat pump to produce heat at the same sort of efficiency with a sort of 2-to-1 ratio. So that's not I don't see that as being a problem. And electricity is much more fungible as a resource than hot water. I mean, there's a subtlety to this that I'll just introduce. The losses associated with circulating water around the building do need to be treated at a high temperature. And so the water goes, we're generating the water centrally and circulating it around the building, and it needs to be reheated when it comes back to the plant room. So it goes out at something like 55 and comes back at 50, and we have to heat it up from 50 to 55. When we're heating, we use some of the heat from the CO2 heat pump to provide that reheat. But in the summer, when we don't have a heating requirement, a space heating requirement, we're achieving that reheat, if you like, with a separate set of heat pumps, which do work efficiently at 55 degrees centigrade. So that's a subtlety.
Okay, maybe one last question.
Hi, I was just wondering about the glass material, There has been work on what we call smart coatings, and they can potentially improve the efficiency, the glass responding to the weather conditions. Now, I was wondering if you looked into that. It may not be cost effective, but it definitely improves the efficiency.
The films that they're using and the coatings are absolutely amazing now. And we have not been, if it's cost effective, it goes onto the market and we hear about it and then we specify it. we're not saying you must use this coating or this coating. We're users, basically. And the U values, just going through, so single pane of glass, the U values of the existing, the old glass is about 5.6. The Q-in glass is, the center pane U value is something like 0.4. It's absolutely extraordinary how much lower it is. Yet, if it was just double glazing, it would be more like 2.8. So to get from 2.8 with double glazing down to 0.4 with the Q-in glass is all a matter of films and coatings and clever stuff that there are guys in universities around the place developing that stuff.
I mean, I think it'd be very interesting in 5 or 10 years' time where the technologies have got to and where the commercialised technologies have got to. But I think given where we are today, this is some of the most advanced technology on the market that we're using. So, I mean, I do hope that in 10 years' time people will be able to do it even more efficiently than we're doing it. But
I find it extraordinary.
it's nice to be on that cutting edge anyway. I think I'm going to draw it to a close there. Thank you very much indeed to Marion and Andrew and to Bill. Thank you to everyone who's come here today. Thank you to those of you listening down the line. I think this is a fantastic journey that we're on. I think we're all a combination of exhilarated and exhausted by it. But I think it's an absolutely necessary journey and one that other people will be taking after us. So I'm delighted to be part of this. Thank you very much indeed, everyone, for being here and being part of this enterprise. Thank you.
Thank you.
When you were talking.
Okay, I need to shoot.
Yes.